Hi, welcome back to this class. It's about differential evolution. This class is a practical example of differential evolution will be implemented in this class. So here's the algorithm: start and then initialize population. And this we will randomly initialize the population. That's randomly initialized population. And then next step is evaluate which individual is the best or find out the best individuals. Then we will have to get the target vector. Target vector will be determined by this equation. The target vector equals x vector plus f multiplied by difference 2 of the populations that we have. And then we do crossover. Of course, we need crossover rate to do that one. And then we will select the genes whereby we use greedy method to select the genes for the next iteration. And then evaluate new population. If the convergence arrived, we will stop. If not, we go back here to get each target vector. As we go through the samples that we have. So that's more or less the algorithm. Here we have the difference between the two vectors, and that is f, which is a factor, and this mutant vector, v. Mutation can be done by here. That's the first step. Crossover can be done in this way. And then the selection process is the greedy method. And we will try to give you the sample. So let's say we have this example, this equation. We will try to minimize this equation. It has three dimensions, x1, x2, x3, all of them squared. And each x will take in between negative 100 and plus 100. So that's the searching range. Population size, we will have 4 samples, and dimension, we have x1, x2, x3, and all of them squared. So that's what we have. Okay, now very simple. Initially, randomization of the solution. So the first solution, initially randomized solution. So we got minus 90, 2, 1. Gene 1, minus 90, gene 2, 2, gene 3, 1. So square of this, square of this, square of this, and sum them, we will get 8,105. Likewise, the individual, randomly we selected this, the individual 2, R2, and these are the genes whereby randomly given 7, 9, minus 50. Square this, and square this, we will get the fitness function. Likewise, that's the fitness function. I should show you that's the fitness function. So all genes, this gene 1, gene 2, gene 3, and these are random values, first iteration were given. All of them these are the fitness function for them. Now, here, step 2, mutation. We will have a choose target R1, and we choose 3 random vectors. For example, R2, R3, R1. So these are R2, R3, R1 will be selected, will be chosen, and R1 is the target choice, and the 3 other R's are random vectors that were selected. Now, this is the mutation equation as I explained. V equals R2 plus F R3 minus R4. Now, this is the R2 that was chosen, and this is R3, and this is R4. So we will, when we have F is set to 0.5, it's a constant. So here is R3 minus R4, the difference. I mean, that's gene 1 minus R3, and R3 gene 1 of R3 is 4, uh, and gene 1 for R4 is 8.5. So the difference of them. Likewise, gene 2 for R3 is 2, and gene 2 for R4 is 7, and gene 3 for R3 is 9.2 minus, and gene 3 for R3 is 9 minus for gene 4. So here the result, these are the, like, so here R3 minus R4, 4 minus 8, 5, 2 minus 7, minus 9.2, minus 9. That's the equation. So that's the result. We got the result. We multiply by 0.5. This is the results of the difference between them. Now we need to add R2 because that's the equation. So we did the difference. We did this part. So still this part is not yet. So we need to add it to R2. R2 is 7, 9, minus 53 genes. Gene 1, gene 2, gene 3. And we added, and now we found mutant vector. Now mutant vector, we have the fitness function. Here is the fitness function. I go back. That was the fitness function. So mutant vector, we plug each gene into fitness function, and we see how we can evaluate mutant vector. The mutant vector that we receive, that we obtained it from this equation, we will evaluate it. And the evaluation is done by plugging each gene into fitness function, 4.75 squared, 6.5 squared, minus 95. So I forgot minus here. Sorry for this. Minus 95, 59.9.1 squared, and we receive this information. So that is the fitness function. Now we evaluate this and we compare this fitness function for mutant vector with the fitness function of of uh, of R1 that we see. So that is the fitness function. So we can see the cross. We'll do the crossover now. The crossover R1 is the target with the V. So imagine the crossover rate is 0.9, and we generate 3 genes. Okay, so we have 0.21. We have crossover 0.9, and we toss 3 numbers for each gene. For gene 1, we receive 0.21. I mean, toss in between 1 and 0 random number. We receive 0.21. We receive 0.97. We receive 0.8. Each random number will be checked against the crossover rate. So if random number smaller than crossover rate, take from mutant, else take from the target. So take from the mutant. If it is random is less than CR, we take from the mutant. We take this gene. If that's smaller, if the random smaller than the crossover, or else we take from the target. We take from here. So let's do it. Let's do it 0.21 smaller than 0.5. That's okay. So we take from the we take 4.79 from mutant because it was smaller than 0.9. Now and gene 2 it happened to be 0.97, the random number, greater than 0.7, so we take from the target. So we take 2. The target was 2. So the first time we took this one, and the second time we took this one. Now we see the R3, random 3, 0.8. That's smaller, so we take from the mutant. So we take minus 59.1, which was mutant, the third gene. That's minus. Remember, we forgot this minus here. That's 1 minus, forget it there. Sorry for this. So now the new vector is this one, the trial vector. It was a product of throwing or tossing three random numbers, and we compare that random numbers with the crossover rate. If it's smaller, we take from the mutant. Or else we take it from the target. So now we try to plug this one into fitness function, and we'll see we receive the fitness function 35193.39, and we compare it this one smaller than this one. The R1 target, remember, R1 was target, the first sample fitness function was 8,105, whereas the trial vector that we received is 3519.37. So it means R1, it means the trial is better than R1 in terms of fitness. So therefore, the trial will be taken, will be accepted, will replace R1, will replace R1, will replace R1. That is the idea. It will replace R1. That was the idea, replacing the R1. And then we will see that is the table that we have it. So R1 was replaced. It's now this value and with less fitness function. Earlier it was 8,000 something, and now it's reduced. So, and then we will do this process over and over for the next iteration until the best result is found. Why DE works well? Because of the mutation, which is through this equation. Mutation was the kind of a good trait, a good property in DE algorithm. Now, the search step depends on population diversity, thus large diversity, large steps, convergence, small steps. This gives automatic step size adaptation, and a neat trick, the population itself becomes the ruler. Now, main difference between genetic algorithm GA and differential evolution DE. Well, genetic algorithm mainly focus on crossover. Kind of mutation is optional, not mainly mandatory in genetic algorithm. Whereas in differential evolution, mutation is dominant. And you see, this is the key. Dominant is the heart of DE. That was the idea. So advantage, simple, few parameters, fast convergence, good global search, easy implementation, strong on continuous optimization. Not ideal, disadvantages for discrete problems. Parameter sensitivity can stagnate on some landscapes. Application, you can use it for all the applications. Unlimited application can be used for DE. And thank you very much for listening. So it was, we started with this algorithm. That is the algorithm. We randomly initialize population, and then we have a mutation vector. Mutation, that's the example that we took, the fitness function, and this is the dimension. Now we have a sample of 4 samples randomly selected, 3-dimension x1, x2, x3. So this is x1, x2, x3. Each x is a gene. So these are randomly given for R1, R2, R3, R4. R1 fitness function is that one is kind of big. And now the first step of the algorithm will do mutation formula, which is kind of, we choose 3 random vectors within the samples that we have. We take 2 of them, we take difference of them, we multiply by F, which is the factor of progress, plus the other chosen sample from the tree. And then once we take the mutation vector, that's mutation, we plug it into the fitness function, and we found the fitness function is this one. Now we will get the step 3 for now. This is improved by mutation. Now we go to next step, which is crossover. In the crossover, we have the target, which was R1, and now mutant vector is this one. For each gene, we throw one random number. We toss it in between 0 and 1. If it's smaller, we will take a part from mutant vector. If it's greater, we take a part from R vector. It's either you take from R vector, the gene, or you take from mutant vector. And this depends on the toss or the random values that you received. Now, that's how we done. And the new trial vector is this one. Now, plug it into fitness function that we have it, and you see that this is reduced. So this solution is accepted. Therefore, R1 has changed. It was replaced by U vector, which was a combination of the mutated vector plus the crossover that we implement on it. So that's more or less on this algorithm. Stay tuned with the next algorithms. Thank you very much for listening. And if you have any problem, please, that's the link so you can send me any questions that you have. Thank you.